You're listening to DTFHN for June 3rd, 2026. I'm your obsessively decompiled host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where people who could be touching grass instead choose to touch hex dumps. Today's full of that slow burn builder energy. Let's crack it open. The name is Edsger, as in Dystro, the computer scientist who spent decades writing manuscripts by hand, who believed that the act of writing, slow, deliberate, physical, was inseparable from the act of thinking. Daniel Janis named his project after that conviction, and the choice tells you everything about what this actually is. On the surface, it's a Clojure REPL running on a remarkable 2. You write code with a stylus on e-paper. Handwriting recognition converts it to text. The expression gets evaluated, and the result appears on screen. 14 seconds from pen lift to output, according to the comments. 14 seconds. In a world that measures latency in milliseconds, someone built a programming environment that asks you to wait. There's a concept in ecology called succession. When a forest burns, the first things to grow back aren't trees. They're small, fast, opportunistic plants. Weeds, essentially. They stabilize the soil. They create shade. They make conditions possible for slower, deeper-rooted species to eventually return. The weeds are necessary, but they aren't the forest. Most of our programming tools are weeds, fast feedback loops, instant compilation, autocomplete that finishes your thoughts before you have them. They're optimized for speed of output, and they're valuable. Genuinely, but they select for a particular kind of thinking, the kind that reacts rather than considers. Edsger is a tree. It's a tool that, by its physical constraints, e-ink refresh rates, handwriting recognition overhead, the deliberate pace of a stylus on paper, forces you into a different relationship with code. You can't spam expressions at it. You have to think about what you're going to write before the pen touches the surface. Every evaluation costs you 14 seconds of your life. So you make each one count, and it runs on a device you can SSH into. The remarkable 2 is Linux under the hood. Open, accessible, hackable. One commenter discovered for the first time that they could even SSH into their own tablet. That's the quiet power of open hardware. Not that someone built a Clojure REPL on an e-reader, but that the architecture of the device made it possible for anyone to try. The blog post itself is handwritten. Daniel's entire site renders his actual handwriting. Pen strokes on the remarkable, exported and published. Links embedded in handwritten text. It's a small act of defiance against the homogeneity of rendered type. And it's beautiful. 14 seconds of latency. Most engineers would call that unusable, but Dystro wrote some of the most important algorithms in computer science history with a fountain pen. Sometimes the delay is the feature. We talked about tools shaping how we think. Pause. Here's a story about one thinking tool that left the front door wide open. A single click. One URL. That's all it takes to hand over read and write access to every private repository on your GitHub account. Here's what's happening. GitHub has this feature called github.dev. You swap .com for .dev on any repo URL, and you're dropped into a browser-based version of VSCode. Full editor, pull requests, commits, the works. To make that work, GitHub silently passes an OAuth token from github.com to github.dev via a post request. And that token isn't scoped to the repo you're looking at. It has access to everything, every private repo, every organization you belong to. Now VS Code has a security model for this. Web views. The iframes that render things like Markdown previews and Jupyter Notebook outputs. Run on a separate origin from the main editor. Cross-origin isolation. The same principle that keeps a random iframe from reading your Google cookies. Communication between the editor and these sandbox frames happens through post message. A narrow channel for passing JavaScript objects back and forth. It's elegant, actually. The architecture acknowledges that rendering untrusted content is inevitable. So it builds a wall and puts a mailbox in it. The problem is that mailbox. Security researcher Amar Edsger found a way to craft a link that, when clicked, exploits the WebView messaging layer to reach across that boundary and exfiltrate the OAuth token, the full chain. From click to token theft. Runs in the browser, silently, with no user interaction beyond that initial click. This echoes something from Mindine88, when Robert Tappan Morris launched the first internet worm. The Morris worm didn't exploit some exotic vulnerability. It chained together mundane Unix features. Fingers, some mail, weak password guessing. Each one reasonable in isolation, catastrophic in combination. Edsger's finding is the same pattern. OAuth token too broadly scoped. WebView messaging designed for legitimate cross-frame communication. 1 million lines of TypeScript with surface area that no single team can fully audit. Each decision defensible on its own. Together, a one-click credential theft. What makes this worth admiring? And I mean the research, not the vulnerability, is the craft of the disclosure. Edsger documented the full chain, built proof of concept, and published the write-up so other researchers can learn from it. One commenter noted that Microsoft's Security Response Center has a pattern of silently fixing reported bugs without credit. Edsger published anyway because that's how security actually improves. Not through closed-door patches, but through shared understanding. The blueprints for the lock and the lockpick. Available to everyone so everyone can build better locks. The fix isn't complicated. Scope the token to the repository. It's the oldest lesson in security engineering. Principle of least privilege. And it's still the one that gets forgotten first. What happens when someone applies that same obsessive reverse engineering energy not to security, but to a 1990 DOS racing game? 32 by 16. That's the grid. 512 cells, each one 2 bytes wide. A tile ID to select a mesh, plus some packed bits for rotation and height. 1 kilobyte to describe an entire world. Test Drive the Row, shipped in 1990. Accolade built a driving game where the point, ostensibly, was racing. But the actual experience, the thing that stuck with people, was that you could just drive. Turn off the road, follow the railroad tracks. Chase a chicken. The world was there, whether you engaged with the competition or not. Sebastian Mack spent 5 years pulling that world apart. This 3D format is straightforward once you understand it. Each tile, or object, is a small mesh. 3 parallel arrays of signed 16-bit integers for x, y, and z vertex coordinates, followed by 8-byte polygon records encoding shape type vertex indices and a palette color. A short header, 4 or 8 bytes, and that's the unit. The constraint these developers were working against was a 286 processor, with maybe a megabyte of RAM and no dedicated graphics hardware. Every byte in that format exists because someone in 1989 decided it had to. Parallel coordinate arrays instead of interleaved vertex structs, because that's how you minimize cache thrashing on a processor that barely has a cache. Packed rotation and height bits in the map cell, because you cannot afford a third byte. What Mac built is a complete extraction pipeline. Node.js tools that parse the original binary formats, LZW and RLE decoders for the compressed assets. A 3.js browser viewer that renders the reconstructed maps in real time. And Wavefront OBJ export, so the geometry can live in any modern tool. The file format specifications are documented in a spec directory. Every data structure, every bit field, every compression scheme, written down so anyone can read it. This is archaeology with a compiler. The original developers left no documentation. The format had to be inferred from binary analysis, from loading the game and watching what changed in memory, from staring at hex dumps until the patterns emerged. 5 years of that, on and off, driven by nothing except the memory of a kid who liked to explore a world that fit in a kilobyte. The whole project is on GitHub. The meshes, the tools, the format docs, the viewer. Someone else can pick this up, extend it, port it, learn from it. That's the thing about open work. It compounds. One person's obsession becomes everyone's reference implementation. The comments are full of people hearing the ad-lib soundtrack in their heads, remembering the railroad, remembering the chicken. 35-year-old software, still alive because someone cared enough to read the bytes. Moving on. Let me work with the article text provided in the prompt. The article is cut off partway through, but I have enough context about the vulnerability chain. Reverse-engineered firmware. No signature checks on updates. Bluetooth attack surface. Bad USB. Capability and the covert spying angle. Let me write the script. What happens when your speaker trusts every stranger in the room? Not metaphorically. Literally. Any Bluetooth device within 15 meters. No pairing required. No physical contact. No authentication. Just proximity and intent. A security researcher wanted to write a Linux tool for their creative sound blaster Katana V2X, a USB soundbar, the kind of thing you set on your desk and forget about. But reverse engineering the firmware pulled a thread that kept unraveling. The speaker uses a proprietary protocol called CTP, Creative Transport Protocol, with challenge response authentication over USB. The key is static, baked into the binaries that ship with the Creative app, but fine, at least they tried. Firmware updates also run over CTP. The researchers sniffed USB traffic with Wireshark, extracted the firmware image, and found 3 components. A bootloader with recovery mode, the main firmware running a modified FreeRTOS PS, and a SHA-256 checksum appended at the end. That checksum is the only protection. No cryptographic signatures. No locked bootloader. Patch the firmware, recalculate the hash. Flash it. The device says, "Thank you." The researcher proved it by replacing the boot screen text from welcome to patched him. Cute, but run this forward. If you can flash arbitrary firmware, you can make the device do anything. Record audio through its microphone. Inject keystrokes as a USB HID device. The classic rubber ducky attack. Your soundbar becomes an attacker's implant. And here is the question nobody at Creative apparently asked. Why does the Bluetooth interface accept commands without pairing? Anyone within about 15 meters can connect and interact with the device. Combine that with unsigned firmware, and you have a remote, wireless, zero-touch attack chain. Walk past someone's desk. Own their speaker. Use it to type commands on their PC. Listen to their conversations. Leave. The firmware runs on FreeRTOS compiled from a developer's home directory. The authentication key is static and extractable. The update mechanism checks integrity, but not authenticity. Every layer of this system chose convenience over security, and the result is a consumer device that can be weaponized by a passerby. This is what closed firmware gets you, not protection. Obscurity. The researcher who found these bugs did it anyway. Imagine if the firmware had been open from the start. 1,000 eyes finding these issues before they shipped. Instead, one person with Wireshark and patience had to do what Creative's own engineers either missed or deprioritized. The tools exist. The researcher published them. That is how security actually improved. Not by hiding the code, but by letting people read it. 5 stories in, and we're just getting warmed up. Let's talk about making your hardware work harder for you. In $9 Killers, the Allah's computer at Manchester introduced virtual memory. The idea was simple, and to many engineers at the time, offensive. Pretend you have more RAM than you actually have by quietly shuffling pages to a drum. Tom Kilburn's team got called crazy for it. 65 years later, a developer on a laptop with soldered RAM and no upgrade path looked at 8 gigabytes of VRAM, sitting completely idle on a discrete Nvidia GPU, and had essentially the same thought. The project is called NBD VRAM. It turns your GPU's video memory into Linux swap space. Not through some exotic kernel module, not through Nvidia's peer-to-peer API, through a Unix socket and the network block device protocol, which has been in the kernel since version 3.0. Here's where the comedy kicks in. Nvidia actually has a proper API for this. Nvidia Position lets you pin VRAM pages so the CPU can access them directly. Beautiful, clean, fast. It also returns IAEN on every consumer GeForce GPU ever made. Gated at the resource manager level. Quadro and data center cards only. You can have the hardware. You just can't use the hardware the way Nvidia's own documentation says you should, unless you pay for the different driver signature. The developer tried the other obvious route too. Directly memory mapping bare 1. The GPU only exposes about 16 megabytes through bare 1 by default, just enough for the display frame buffer. Reads from the rest, return zeros. MKSwap says it worked. Swappin says it didn't, and you've just learned more about GPU memory architecture than you wanted to. The NBD approach is the one that actually ships. A small daemon allocates VRAM through the CUDA driver API, which works on any consumer card with no special permissions, then serves it as a block device. The kernel sees a normal swap partition. The result on a laptop with 16 gigs of RAM and an RTX 3070-60. 46 gigabytes of addressable memory. Triple what the machine shipped with. Overflow priority is RAM first, then VRAM over PCIe, then SRAM compression, then SSD as a last resort. Run this forward 5 years. Laptops keep shipping with soldered memory. GPUs keep getting more VRAM. The proper API stays locked behind enterprise licensing, and someone's Unix socket hack becomes the standard way to use hardware you already own for the purpose it's already capable of serving. The gatekeeper didn't stop the builder. The gatekeeper just made the solution more creative. Moving on. One commenter put it perfectly. They said the press release title should have been something like, "For Common First-Year Contracts Law Questions." Law professors preferred AI-generated answers to professor-written ones, which, yes, is more accurate. But the deflation tells you something. When results challenge assumptions, the first move is always to shrink the claim until it feels safe again. Here's what actually happened. 16 law professors across major U.S. institutions wrote answers to 40 contracts law questions. The kind students ask after class, during office hours, then they blind evaluated those answers against AI-generated responses. 3,000 head-to-head comparisons. I won 75% of them, and professors flagged AI answers as pedagogically harmful 3.5% of the time, versus 12% for answers written by their own colleagues. The study designers at Stanford, Yale, NYU, and Chicago did something smart. They calibrated AI response length to match human answers, eliminating the usual complaint that AI just buries you in text. They picked law specifically because it resists simple right or wrong evaluation. Two opposing arguments can both be good. The question was whether AI could meet what the researchers called the latent professional standard. The gut-level judgment lawyers used to evaluate reasoning quality. It did. Now, the bootstrapism angle here is unmistakable. Office hours at a top law school are a scarce resource. You get access if you got admitted, if your schedule aligns, if you're comfortable approaching a professor. An AI tutor that meets professional standards doesn't replace the professor. It makes the professor's judgment available at 2 a.m. to someone studying in an apartment who couldn't afford test prep, let alone Yale tuition. One commenter raised a fair point. 16 professors is a small sample. That's worth noting, but the direction of the signal at 75% preference is hard to dismiss as noise. What I admire about this work is the rigor applied to a domain where rigor is genuinely hard. Measuring quality in ambiguous reasoning is a design problem, and they engineered a clean one. The tools exist. The question, as always, is whether institutions will put them where students can reach them, or keep office hours behind the same gates that built the prestige. Microsoft just dropped a coding model that's small, fast, and punching way above its weight class. I've spent enough time wiring models into agentic loops to know that the gap between benchmark performance and production behavior is where most promises go to die. A model that scores well on isolated tasks can still fall apart when it has to coordinate tool calls, manage context, coarse files, and recover from its own mistakes inside a real harness. Microsoft clearly understands this problem. Their new MAI Code 1 Flash was trained directly inside the GitHub Copilot production harness, evaluated on checkpoints drawn from real usage telemetry. That's a sound engineering decision. Train where you deploy. Evaluate what you ship. The adaptive solution linked control is genuinely interesting. Letting the model calibrate its reasoning depth to task complexity means you stop paying full thinking prices for simple completions. 60% fewer tokens on hard problems while maintaining accuracy. If that holds in production, it's meaningful for anyone running these models at scale. But here's where the architecture question matters more than the benchmarks. This is a 137 billion parameter mixture of experts model, with 5 billion active parameters. The commenters notice something important. Qwen 3.6, an open model at 35 billion parameters with 3 billion active, scores within 2 points on STWI Bench Pro, 49.5 versus 51.2. For a model, you can run yourself inspect, fine-tune, deploy on your own infrastructure without a single I call derailment. Microsoft trained this model on production Copilot data, which means it learns patterns from how developers actually use Copilot. That's a feedback loop that only works if you control the platform. The model gets better because it sees your workflows. Your workflows get routed through their infrastructure because the model gets better. This is the kind of closed-loop dependency that looks like optimization from the inside and looks like lock-in from the outside. The benchmarks they chose to highlight tell their own story. Comparing against Haiku 4.5, a model designed for speed and cost efficiency, not peak coding performance, lets you claim wins that wouldn't survive a comparison against the models developers actually reach for when the problem is hard. I respect the engineering. Training in harness is the right methodology, and adaptive token budgeting is a real contribution to how we think about model efficiency. But the open source ecosystem is closing these gaps with models you can actually own. When Qwen matches your flagship coding model at a fraction of the parameters, and anyone can download the weights tonight, the value proposition of a proprietary endpoint starts looking thin. The tools exist. The weights are available. The question is whether you want to rent your intelligence or own it. Now, if you think open source AI is revealing hidden efficiencies, wait until you see what nature's been hiding in plain sight. Billions of protein sequences. Surely that means billions of unique structures to train on. The scaling laws say more data means better models. And genomics has handed us an ocean of sequences from organisms we've never even cultured. The recipe writes itself. Fold everything, train on everything. Watch your enzyme design model get smarter. More sequences, more structures, more capability. This is the logic that built modern AI. Logabio followed that logic and hit a wall when they clustered the known protein universe. And the engineering here deserves attention because clustering billions of sequences at structural resolution is a serious computational problem. They found that natural fold space is radically more compressed than sequence space suggests. Millions of distinct amino acid sequences collapse into a comparatively tiny number of structural topologies. Evolution, it turns out, is not an explorer. It is a conservator. It found a set of folds that are thermodynamically stable, mutationally robust, and easily foldable. And then it played variations on those themes for 4 billion years. Follow the scaling argument to its logical extreme. If you could fold every protein sequence ever produced by every organism on Earth, how much new structural information would you actually gain? The answer, based on LEGO's analysis, is dramatically less than the sequence count implies. You're not adding new structural diversity. You're adding redundant projections of the same fold topologies onto slightly different sequence background. This matters for anyone training generative models on biomolecular structure. The bottleneck is not sequence coverage. It's genuine structural novelty. And that realization reframes the entire design problem. If nature only explored a fraction of viable fold space, then the structures we most want to design, novel Menzanes, unprecedented binding geometries, may live precisely in the regions evolution never visited. What makes this work valuable is that LIGO published the analysis, the clustering methodology, the redundancy metrics, the implications for training data strategy. It's all there for anyone building in this space. 1,000 teams can now calibrate their own data pipelines against these findings instead of independently rediscovering the same ceiling. That is how the field accelerates, not by hoarding insights about the shape of the problem, but by mapping the territory and leaving the map where others can find it. So what happens when all these open maps, open models, open tools actually reach the people building things? Story 9. Scroll past the names everyone recognizes. Torvalds, Carmack, Bellard. And look at the bottom of this list. A Swedish blogger named Johannes Ritterstedt ends his post by listing 5 programmers you've almost certainly never heard of, and then offers his own email address as a starter. Send him a note. He'll point you somewhere. That's the detail worth pausing on. Not the celebrity roster. The on-ramp. Let me play the counter-argument for a moment. You could say this is naive. These people are busy. Cold emails are noise. Linus Torvalds famously does not suffer fools. Emailing your heroes is a recipe for a polite non-response. Or, worse, the Chomsky reply. One commenter describes writing to Chomsky and getting back essentially, "I probably won't read this. Why would anyone bother?" Because the math works differently than you'd expect. One commenter wrote to Mike Paul, creator of Luajit, and got what they called a refreshing reply. Another points out that Daniel Stenberg, who built curl, is actively conversational on LinkedIn. The barrier isn't access. It never was. The barrier is the assumption that access requires permission. And this is where the clinical observation matters. The people who built rawsync, Git, FFmpeg, Quiu. They didn't build those things inside institutions that gatekeep interaction. They built them in the open. The mailing lists are public. The commit logs are public. The conversation is public. One commenter realized they could just start posting to an OSS mailing list. No introduction necessary. And that changed everything for them. The loneliest comment comes from someone who spent 2 years working alone in a windowless room. The antidote wasn't a better job. It was participation. Every name on that list built tools that millions use daily. Every one of them is reachable. The infrastructure of open source isn't just code. It's the radical accessibility of the people who write it. Moving on. Lumafield put a BYD key fob into a CT scanner. What they found inside was essentially a Russian nesting doll of vertical integration. The battery, the circuit board, the mechanical backup key. Every component manufactured by BYD themselves. A key fob, the thing you lose in your couch cushions. Now zoom out. They scanned the brake calipers, the motor assembly, the battery pack. Same story at every level of magnification. BYD makes the chips that control the motor, that's powered by the battery cells they manufacture in factories they built on land near lithium mines they own. The last company to attempt this kind of womb-to-tomb manufacturing was Ford, back when the Rouge River plant turned iron ore into Model A's on a single campus. Think of it like a coral reef. Most automakers are ecosystems. Thousands of independent organisms, loosely cooperating, each optimizing for its own survival. BYD is the reef itself. The substrate and the organisms are the same creature. That's either terrifying or magnificent, depending on where you stand. The CT scans reveal something the spec sheets can't. The tolerances are tight, the castings are clean, the engineering is earnest. One commenter, an HV-certified mechanic, has a BYD Shark torn apart on his workshop floor and keeps finding details that impress him. Here's the uncomfortable part for legacy automakers. BYD isn't winning on one thing. They're winning on the integration. When you control every layer of the stack, each improvement compounds. That's a lesson the software world learned decades ago. Hardware is just catching up. The scans are public, by the way. Go look. This has been your daily tech feed for Hacker News for June 3rd, 2026. This podcast is entirely AI generated. Scripts by Claude Opus 4.6. Voiced by Quen3TTS. Not affiliated with Hacker News or Y Combinator. Now go build something and leave the door open behind you. We'll see you back here tomorrow.